Thank you. Hello, everyone. So my name is Amine. I'm PhD candidate at Columbia University, and today I will be talking about sample-based optimal pricing. And this is a joint work with my advisor, Omar Besbes. So let me get started by motivating why we are looking at pricing. So pricing is important across different industries, and since it's decision variable that the seller would use to maximize, for instance, the revenue. And in our talk, we will focus on revenue maximization. But while making this decision, there is one key element or key input, which is that the seller needs to take into consideration to set the right prices, which is the distribution of the willingness to pay of the customers. So in practice, this distribution is really not available. So one approach is to use the available data on hand in order to set the right prices. So this leads to data-driven pricing. And there are different levels of data-driven pricing depending on the information or data available. So in this slide, I will try to summarize different approaches that have been discussed in the literature. So the first one is the full information, meaning that when as a modeler, we know the exact distribution of the willingness to pay of the customers. And this is in some sense the Oracle benchmark. And also there is the other regime when we know a little bit about the less about the distribution of the willingness to pay. And there is a stream of literature that has looked at the case when how many samples do we need or observation from the distribution in order to be epsilon close to the optimal or the Oracle revenue. And also there is another dimension across which there are different works about data-driven pricing, which is the time horizon. And so there is the short time horizon, meaning the static one time period, as well as the dynamic version of data-driven pricing, where as a seller, we try to collect the samples on the fly and try to find the optimal selling or price by exploiting and exploring the data that we have. And this is these typical studies would try to characterize some regret bounds as function of the time horizon. As well, there are other dimensions that data-driven pricing literature had looked at, like a constraint or about commitment and so on. In our work, and we look at the growing stream of literature that really look at this fundamental problem where we have really limited data about the distribution of the willingness to pay, as well as we look at just the basic case, which is a one time period. So we are not the first one to look at that. There has been a growing literature, as I mentioned earlier, and one stream is pricing without prior, and more closely it's the small sample regime, and I will mention more precisely how our work relates to those works. And also, as I mentioned, it relates to this online or pricing while learning. So in the rest of the talk, I will formulate the problem. Then I will give you an overview about our results. Then I will try to give you, depending on the time, the details of the approach, if the time permits, as well as the challenges that we have. Then we'll conclude. So the problem is fairly simple to state. So there is one seller trying to sell one indivisible good to one buyer. And this buyer has some willingness to pay. It's a value drawn from some distribution F. So here, what we will assume is that we don't know the distribution F, but the seller has access to one observation or to one sample from this distribution F. And the goal really is, given this sample that we have observed, is to try to post a price for this buyer using this sample. And one way to formulate that is that the pricing strategies that we'll consider are randomization over different prices that we could post given the sample. In other words, so as a seller, I will observe a sample, then I can pick randomly different prices. I can pick a deterministic price as well as I can randomize over different prices. Here, the goal is that we allow for general pricing mechanism. We'll make a small assumption that this pricing mechanism are well behaved around zero. This is more for proofs detail, but it should not hurt our results. So, but the main idea here is that conditional on observing a sample S, I will post or a price according to some distribution psi. So this is the model. So now, given this model, let's look at our revenue. So the revenue, let's read it from the inside here. So P is the price that we'll post to the customer. So we'll make P with probability whenever this customer can pay this price. So it's P times the CCDF of P. But we can randomize over the price. So this first integral just is averaging over randomization that we are taking. And we are making the decision psi. And each decision we can make it because contingent on the sample that we have observed. And also we average over all the sample to get something that we can evaluate. So here, not in this quantity, we cannot evaluate it because we don't know F. So we'll need to introduce some benchmark, and we'll compare this revenue to some Oracle benchmark. And the Oracle benchmark that is the one that knows the exact distribution. And this is the optimal revenue had the seller had access to the exact distribution. And the performance of a mechanism psi will be, against some distribution F, will be the fraction that this mechanism psi is able to extract from or compared to this Oracle benchmark. In other words, if this quantity is equal to 50%, for example, it means that our psi mechanism is able to achieve 50% of the optimal. So we'll assume that we know some admissible class of distribution that I will specify later. And the related performance is the worst case performance against this class of distributions. So the goal or the objective of our work is to find the max mean ratio. In other words, as a seller, I would try to find a mechanism that maximizes the worst case ratio. So this is the goal of this talk. So now I need to just to specify what classes we look at, admissible classes. So for that, I will just remind the definition that was introduced earlier in the literature. So a class of alpha strongly regular distribution is a class such that the virtual value function is increasing, and the slope of this virtual value function is greater than alpha. Meaning that the difference between two values is alpha times the difference at two values. So why we look at this class of distribution? As I mentioned, it was already introduced in the literature, but also, more importantly, it contains two classes that are widely used in the literature, which are the regular class of distribution, and this is when alpha equals to 0. And also alpha equals to 1 is the monotone hazard rate class of distribution or increasing failure rate class of distribution. And why we look, typically we look at this class of distribution, because for these classes of distribution, we can characterize exactly what is, if we had known the distribution, we can characterize what is really the optimal price. So there is only one price that we can post if we had known the distribution. But here we don't know the distribution. So really our objective in this paper is to characterize this max mean ratio for each alpha. And we'll try to provide a uniform characterization. Okay. So our contribution are, so the first our approach will be unified across all the alphas, and will give a systematic approach to characterize this max-min ratio and the near-optimal mechanism. How do we do that? We draw a connection between pricing literature and the literature of statistical theory of reliability. And this is how we are able to give a uniform approach. So we are, as far as we know, we are the first to provide impossibility results against randomized mechanisms. And also for regular and MHR, we give tighter guarantees. And we are the first, I think, as far as we know, is that for alpha dependent, we give really alpha dependent characterizations. And last, which is also important, is that we show that we characterize the power of randomization. Does Cedar, is it worth it really to randomize over prices or not? And what we show across our studies is that the power of the randomization is not that big. And I will be more specific in a few minutes. So in this table, I will now go back to the papers that I have mentioned earlier. So in this table here, I will try to characterize the maximum ratio and give you a flavor of our results. So here we have different classes of distribution. So I will provide you the best known lower bound and what we provide, and the best known upper bound and what we have improved. So let's start by the regular class of distribution, which is the big class of distribution. So what is known is that by Hufu, Bernard Lussier, Nicole Emorleka, and Philip Strack, that there is a mechanism, randomized one, that achieves 50% plus 5 to the 10 minus 9 as a guarantee, meaning that this mechanism, in the worst case, will give this guarantee. One sample. Exactly, one sample. In our paper, we improved this lower bound to 50.1% using one sample. But our contribution does not rely only on improving. We can try to continue improving. But really what we show is that there is no other mechanism that can achieve more than 51.1%. So we are able to characterize the optimal maximum ratio within almost 1%. Okay. For the upper bound, what was known is there was no result for the deterministic. For randomized, there were only deterministic. I will mention that in the next slide. But let's move to the MHR class of distribution. For MHR alpha equals to 1, what we show is that what is known by Timraf, Gardner, Huang, and Mansour is that there is a mechanism that uses one sample and will achieve, in just MHR, in the worst case, 58.9%. Okay. So in our work, we improve also this one from 58 to 63.5%. And more importantly, what we show is that there is no other mechanism that can achieve more than 64.8%. So this is like really the fundamental contribution, is that against randomized mechanisms, we are able to characterize what is the best that one could aim for. Yes, that's right. So and lastly, what I would like to emphasize is that also we provide bounds on alpha regular that we can see now in this graph here. So here what we have is the alpha, and here we have the bounds on the upper bound is the blue line and lower bound is the red line. So if alpha is equal to 0 at regular, and if alpha equal to 1 we are at MHR. And our approach applies to any alpha. And here we give just like examples here, and we see that our approach is very tight. So what are the challenges that one has in order to solve this problem? So first of all, think about, as a seller, I can post any pricing strategy given the sample that I observed. So as a seller, I'm optimizing over infinite dimensional space of mechanisms. So one key step in our paper is to show some reduction to some specific and more tractable set of pricing mechanism. Then given this reduction, we go to the nature problem, which is the infimum. And even that one alone also is not tractable because the nature is also optimizing over non-convex set of distribution and also infinite dimensional. So how we do we deal with that? So it's not even clear how would one approach this numerically. So in the next slide and few minutes, I will try just to give you a high level. I don't think I will have time to go to the details of the books. So how do we develop the tractable approach? As I said, we do this reduction. So instead of looking at any pricing mechanism, we can show that without loss of optimality, the optimal strategy will be just take the sample and multiply it by some factor gamma. And now, instead of looking at any price, you will randomize over this multiplicative gamma. Now, this helps, but now we look at the lower bound. So for the lower bound, so this distribution, lower bound, we are looking at the worst case. So looking at any distribution is almost untractable. So we try to pin down the distribution to some specific quantiles, and we try to understand the local contribution of each interval, that's where the optimal price is. But the idea is that we move from local contributions, like small intervals, using this statistical theory of reliability, this connection at local level. Then we have this small local contribution. Then we sum up them using a dynamic programming that we pick carefully. Then we have a tractable lower bound. This is, in high level. But also this allows us to find, through the lower bound, we are able to find what is the worst case family might look like. So we take those worst case families and we plug them to the upper bound in some sense. And through this upper bound, we are able also to reduce, using the first reduction I mentioned, and this worst case family, we are able to have tractable upper bounds. And so what is the main idea is that we jointly develop lower bounds and upper bounds at the same time. And this was crucial to get these results. And so here in this table, I will just show you some last minute. I will show you just here is that one important thing is that we're able to explicitly find what are the near optimal mechanism and their structure explicitly, as well as the structure of the worst or near worst case distribution. And for example, sometimes the bounds are very tight. So for example, if we look at alpha 0.2, we are almost at 0.4%. And this is mainly due to more numerical evaluation. And there is, non-trivial part in the paper, how do we evaluate these bounds? It's not even clear, even if we get them. So I think, I think I will jump to the conclusion. So mainly this problem is that we have one sample, and we try to allow for any pricing mechanism, and we try to characterize what is the near optimal mechanism as well as what are near worst case distribution, and as a result, we are able to characterize the maximum ratio. So now, given that we understand better this problem, there are many directions that one could explore. So first is, natural one is what happens if we have 2 samples, 3 samples. And the EC of last year, 2018, there was a paper by Babayouf, and that they show some preliminary result on that direction. Also, here we assume that we observe the sample. So one thing is, what if we just observe by or not by decision? So thank you very much for your attention. Thank you.